appears to make the storm want to move to the northwest as well. So as a result, it moves to the northwest, and it does so pretty quickly. In case B, the beta drift is still trying to push the storm to the northwest, but the heating is now not only trying to slow the storm down, it's also trying to change the direction. So getting the heating details within the core and near the core is actually very important in this case, and it appears to be because that if the winds at outer radius are relatively weak, you tend to get storms that might be much more sensitive to how you're dealing with the microphysics and the heating and other things relatively closer to the storm. So this is 8 similar plots, average tropospheric vertical velocity for 8 different cases, and basically we see all sorts of different variations here, and I think the point is that all these little differences are actually adding up to be a lot of different stuff. Okay, so let me just throw the summary on here, and thank you for your attention.
We have time for a question. Any questions?
It's very nice work, and enhance our understanding of how the structure size change across the synchronous world in addition to the motion. My question is, in nature, we always have the cloud radiation forcing, but what determines the size of the real tropical cyclones? Do you have any implication from your results?
Okay, so basically, I think I can address the question by saying one of the things that is definitely different amongst the simulations is the size of the storm, at least with respect to like the radius of the maximum damaging winds and things like that. The width of the core, the radius of maximum winds does vary, but the bigger difference is basically in sort of like the larger scale structure. And that does appear to be, from the cartoon that I tried to show, at least influenced by microphysics through the radiative process. Because what I basically was trying to argue is that by cooling and above warming due to radiation, those heating and cooling rates are really not very large. And you know what, they're not even large enough to get me out of bed in the morning, okay? It's just not really all that interesting. But I played around with heat sources, and if you put in a heat source and a heat sink like that are very similar, it tends to produce a radial outflow. And that radial outflow will basically will invect humidity and hydrometeors out, which then cause more cooling and warming and things like that. So I think that's an element of what's going on.
My question is not, say, the maximum works quite well. But my question is, in the nature, we always have the cloud radiation forcing.
Yes.
What causes the size change of real tropical cyclones?
Okay. Well, so I think that part of what I said is a part of the answer. I think it's a very small part of the answer, and I think you've raised a very interesting question. Okay, so it's something that really needs to be examined. So, but I think the answer is we don't know everything.
Okay. And also the asymmetry of the diabatic heating. One is in the northwest side, one is in the southeast side.
Yes.
So what determines the asymmetry?
Well, that's another very good question. In fact, having the asymmetry more on the southeast side makes a heck of a lot more sense to me, because the convection should be stronger on the southeast side because of the vertical shear that develops due to the beta drift. So why is it in the northwest section on one side? Okay, that's a really good question. And the last picture that I showed of those 8 different structures, so you've seen that picture before, and basically what that means is that somehow the cloud radiative forcing playing around with the billion degrees of freedom that we have in even the simplest models is giving me different structures. And these structures may only seem slightly different, but it appears that these slight differences really can mean something.
Yeah, this kind of follows a little bit on Yu Qing's question. Given the fact that you do have a billion degrees of freedom, as you said, which I agree with, it's really pretty impressive and frightening in a way to see how sensitive your simulations are to these seemingly minor changes in your parameterization schemes. So my question for you is, what would you propose to be a good methodology to determine which one is right?
Okay.
How do you evaluate the model is my question.
Well, I think that's a very good question. So I've been working with people at the Jet Propulsion Laboratory trying to get satellite measurements of things like diabatic heating and whatever in order to try to get a handle on which, first of all, I think all of the simulations are by natural fact, they're all wrong, but some are less wrong than others. And I think that by comparing these things to the observational data more rigorously, we may find ways of tuning the microphysics and the interactions up. The big thing that I get out of this is actually, I think a lot of idealized studies have concluded that microphysics doesn't really mean anything. And what I'm getting out of this is because a lot of idealized studies neglect the cloud radiative feedback. And the surprise that I found here is that it's really playing a big part of the story, much more than I would have guessed.
Okay.
Last question.
Should be a short one.
Okay.
Yeah. The general understanding about the motion is that, roughly speaking, about 70% or more than that of the variability of the track is decided by large-scale mean steering flow.
Yes.
Well, Ross knows about that very well. So, if we are under the regular steering flow, what is the ballpark estimation of the effect due to the asymmetry through these microphysical and radiative processes?
Yes, thank you for raising that point. So what I had done was I'm trying to make basically a model as simple as possible. So I'm trying to remove things like the large-scale steering flow, and of course we need to add those back, okay? So I can't give you a quantitative estimate, but I think that there are factors that would tend to mitigate but also amplify the problem that I've just shown you, okay? First of all, if you have a relatively strong steering flow, I expect all the storms basically to move in the same way. It's not going to matter what your microphysics are and your cloud radiative forcing. But in cases like Hurricane Rita, which was the first case that I looked at, that was a relatively weaker steering flow environment, okay? And the way I say that this can amplify is one particular track may lead it closer to land over cooler sea surface temperatures, maybe to a place where the vertical wind shear is present and different. So you'll see that actually these tracks actually diverge in that situation.
Okay, we had last very good discussion, but we have time limited, so let's move on to the next